Live from the North Carolina Museum of Natural Sciences in beautiful downtown Raleigh, it's the Science Cafe with your host, Chris Smith.
That's me. Hi, everybody. Good evening. Welcome to the Daily Planet Cafe here at the North Carolina Museum of Natural Sciences. I am so glad that you are all here with me tonight on a Thursday night here in the Daily Planet Cafe, because we're going to do some pretty cool sciencey stuff. Who likes science? Okay. I'll just assume the other half of you just like the food at the Daily Planet Cafe. They stayed open late, so you came on in. You're just having dinner, and you happen to have found yourself in the Science Cafe, where we think science is fun, cool, awesome, and everything that is good in life has some science in it. And here at the Science Cafe, it's our job to find out what's good and awesome about it and figure out how it's relevant to our daily life. We do that every Thursday night right here in the Daily Planet Cafe with our program. So every week for now about 6 years, we've been bringing in guests and experts from all over the world in some cases, but most often folks who are pretty local to right here in the Triangle. They come in and share with us a little bit of their expertise, what they know a whole lot about. And then we get to learn something new. That's fun. That's one of my favorite parts. But then also, after the presentation, we flip the script, and you get to ask your questions of our guest speakers. So they get an education, too, in sort of what people out there in the world are thinking about, the things that they think about. What do we know about it, and what do we need to know more? How can we fill gaps in our knowledge? And that's what makes this particular event, I think, so great. And I'm glad we get to do it every week here at the Museum of Natural Sciences, which, by the way, was recently named, again, the most visited historic attraction in North Carolina, which is sort of weird because the Biltmore doesn't have to tell anybody how many people go and visit. So out of the organizations that have to tell people how many are coming, we're at the top. We're also ranked one of the absolute best. We're the largest museum in the state, and it's because all of you people come out, support, and are a part of everything that's going on here every single year. In the last year, we serviced more than 1 million people coming through this institution. That, I think, is incredible, and happens because of you folks doing stuff like this, and we're glad that we can put it on for all of you. Now, tonight, we were having a conversation, our guest, and he was talking about his presentation, and he finished up by saying, yeah, everybody likes fire. Who likes fire? It was all the young people. It was all the young people in the crowd. The rest of us are like, well, you know, maybe in a particular context, and in tonight's context, we're talking about wildland forest fires, big places that catch on fire and can do a lot of environmental damage, right? We want smart people paying attention to those things and thinking about them and thinking about how they impact us, and in particular, how they impact our health and not just the environment as well, right? I mean, if you think about some of the major wildfires that we see happening out on the West Coast from time to time, or even here in North Carolina or close by in Tennessee, right? Just a couple of years ago, there was some major wildfires just in the Smoky Mountains, right? Right, so those things impact us all the time. And then, you know, after these wildfires, NASA publishes satellite photos, and you see these smoke plumes rising into the atmosphere, and we can see these things from space. So to think that the effects of these things are small or localized would be kind of naive, right? Like, we're all going to be dealing with these things as time goes on. And fortunately for us, Dr. Joseph Wilkins at the U.S. EPA is thinking about those things. He's our special guest tonight. So I want you to put your hands together and welcome to this Daily Planet Cafe stage, Dr. Joe Wilkins.
Thank you. Thank you all for coming out tonight. Forgive me for the microphone. It's going to run in and out. But today I'll come to you to talk about fires and to kind of give my take on things, as I've gone through the research over the years, over 10 years of experience with this stuff. So bear with me today as I try to synthesize that into a small presentation. Slight disclaimer, sue me, not the EPA. So I work there. And we got to tell folks that, you know, this is my views and not theirs. So, excuse me there. I'd like to start the talk off with my own motivation. So I think we all have to figure out what matters to us in this world, right? What matters to us, what makes us do what we do. And this picture here, if you can see it on the left, is kind of why I do what I do. So let me explain that briefly. Growing up in Louisville, Kentucky, there was several different power plants, smoke plants, rubber plants, and maybe about 60 or so of them within maybe like a mile radius of my home that I grew up in. So every day when I was playing outside, or when I was fighting or wrestling or with my family or having picnics, the picture on the left is what I saw essentially. So it was always just a reminder that something is in the air, right? So imagine growing up with that. So this is kind of what led me into doing this whole scientific part of air quality, because I also had asthma. So with asthma, you can't go outside all the time because of bad air. So my mom would always say, oh, it's 100 degrees outside, it's gonna be bad pollution, you can't go outside. So as a kid, being 7 years old, hearing this, it's kind of annoying, right, to say the least. So it's kind of like, no, it's clear, it's a hot day outside, I see the sun, let me go. And she's like, no, you will pass out, die, or something will happen to you. So this is kind of why I try to fight pollution and fight fires. And as you can see, it's about 40% on average per year of folks that are dealing with this same type of problem based off where they live alone. So this is why this is important to me. I got to give a brief background for those non-scientific, non-chemistry folks, and I won't go too far into chemistry because this is not school today, but you have two of the main molecules and particles that you have to worry about, and these are ozone and particulate matter. And what those two things do is they mostly get inside our air, inside our lungs, and they cause different things to happen to us, such as bronchitis, emphysema, and other things that can cause lung issues. So we have to worry about those things. And where those things come from is, if you look outside the window, there's cars, there's smoke plants, there's power generation. So every time you plug that iPhone in or that Android, you're adding to the problem more or less. And as humans, we're more selfish and we're not gonna stop adding to the problem. So we have to figure out how to limit that problem and how to create other ways of generating power and things like that. So what we try to do is to understand what we can do about that. So if you can look at the image, you can see that within the air that we breathe, which is the troposphere, there's a lot of things that generate ozone and PM, such as what I mentioned, natural as well as human caused. But above that layer, which is in the stratosphere, you have good ozone. So this is where you hear things like, we need more ozone, the ozone hole is going away. And that's where the ozone is essentially blocking the sun rays from getting to us. This is why you have to wear that SPF 50 and all this other stuff. Because when the harmful rays get in, they kill us, right? Well, more or less over time. So to get into the fires, I'd like to give a brief history on the importance of fires and where kind of how things got to where they got to today. And we have one of the deadliest fires, and it's not really well known, and I think it's not really well known because of where it happened at and when it happened. For most of us, we can't fully pronounce the name of that city. I don't know if you guys can pronounce it, but I can't, right? So it's a lot less easy on the ears versus the Great Chicago Fire, which happened at the same exact time. And Chicago is a lot bigger city than Peshego, right? So most people don't know about that, but it actually was one of the deadliest, and 2,500 people died. This is around the same order as what happened in 9/11. So if you can put that into perspective, that's a lot of people that died in one incident over a short period of time. This is less than a week that we're talking about here. So next we have the largest single fire that has happened. And this one was, I have to kind of thank this fire / I hate this fire because it started the entire career that I'm working in now. This was 5 years after the U.S. Forest Service happened. If you remember back in your history books, Teddy Roosevelt started this great initiative to rebuild the forest and to spark a new change to where we care about the environment. We're more aware of it as a government, as a country. And 5 years after that, one of the largest fires in history happened, to where from Washington State all the way down to Montana, essentially a fire blazed across the entire country. And 3 million acres were burned, and the reason why it was so well known, several books have been written about this thing, is because everyone was enlisted to help. So imagine you're a 7-year-old child all the way up to your 50, 60-year-old parent or grandparent having to go help fight a fire, because there was no fire service then. There was no real forest fire firefighters like we have now. There was no smoke jumpers. There was no hot shots fire team. There was none of this back then. And it essentially was just anyone with a shovel can come help. Anyone who can lift, anyone can knock on a door, go tell someone to run away, from their home. So this is kind of why the Forest Service became the whole vow to fight all fires. And you get things such as Smoky the bear, only you can prevent forest fires, and things like this come about from that. And that's kind of how that history works. And as Chris mentioned, one of the most recent fires is the Great Smoky Mountains fire. So most of you might be familiar with this if you've looked at the news like 2 years ago, or 3 years ago now. This fire essentially is well known because it went through a well-visited area and a area that was full of tourists essentially at the time. So imagine being on vacation with your family, you've paid all these thousands of dollars to go to a tourist area, and you have to be evacuated because the fire is a couple feet from your cabin. And this is essentially why this fire got so much notoriety in the news. So this is kind of why we still have this initiative to fight fires and to do things about fires and to study these things, because it's still happening today just as much as it was back then. We might have more technology and we have, as you see, fewer deaths, but we still have a pervasive issue that we have to deal with. And this is one of my personal favorite slides. So you guys can take a second to look at that. It's essentially funny because you have skeptics that say that, we don't need to do anything about the changing of the climate and things such as that nature, words I can't pronounce or say at this point, I should say. But you have an issue where 90% of these fires are caused by humans. So most of those fires you just saw were started by an illegal campfire that went awry, or someone who threw a cigarette butt out, or someone who just had a campfire in the backyard and it just propagated from there, or someone who was trying to burn some plants or something in their backyard, or a brush fire, and it just gets out of control. And next thing you know, you're at 100,000 acres and you can't stop it. But the funny part about this is that, when they say a bear is out there lighting matches in the forest, it's essentially, a funny way of saying people don't really know how they start. And a lot of times we can't track down who did it. So you don't know how the fire started. And yes, there are some natural ways where you have lightning that starts fires, but this is few and far in between. There's a natural process to these things, but the natural cycle is not as strong as the human cycle. But there is a balance to nature, right? So everything has a positive, everything has a negative. So a lot of us, originally when we looked at fires back in the day, the scientists didn't really understand the full positive sides of the fires. And there's a lot of positive sides. So I didn't fully get it until I went and did an experiment in Kansas, and we were lighting grass fires. And when you can see these deer and these cattle running towards the fire, when you're trying to go away from it, it kind of throws you off a little bit. And the thing is, the scientists there told us they think food. So when the fire burns the grass, within a couple days, fresh green grass full of nutrition comes up. So when you guys go to the store, to Harris Teeter or wherever else, and you see this grass-fed beef, this is essentially what we're talking about. This fresh nutrient grass that helps these cattle grow 4 times stronger than they do anywhere else. And this was in Kansas, so it happens all over the world where they burn these fires for that purpose. And so you have fire-positive things such as that. And then you have fire-negative animals such as ourselves, as well as chicken and bats, things like that, to where it kills their natural habitat that they live in, and it destroys them, and they have to run away. So moving on with that, kind of the same idea. You have plants that are naturally thrive in fire environments, and you have plants that don't. So you have some forests, such as the one in Gatlinburg, that burns on a 50 to 300 year cycle. And when fire rages through there, it typically destroys everything. It erodes the soil, and it causes issues to where it can't really replenish that well. And then you have, on the contrary side, mostly in the Pacific Northwest and California area, the Seattle, Washington area, where you'll have a lot of fires that burn every 5 years or even more frequent than that. And these are really massive, large wildfires, but the plants there thrive on that. They need that to happen. So, like, I'll give you an example. There's pine needles on some of these plants that they can't germinate and they can't reproduce another tree until they get over 150 degrees or higher. So this is something that you have to take into account. There's scientists that literally put these pine needles in stoves in order to germinate them in their labs. So this is kind of something that is fire positive. And a lot of times people think wildfires burn everything, and this is often not the case. It might rage through and it'll just scar the outside of the trees. So if you look at some of these tree rings over the years, you can see when major fires happened in the tree rings. And this is another aspect of science that people do in ecology. So this is kind of one thing that if you don't fully understand the difference between a wild and prescribed fire, you're not alone, because everybody defines it differently, which to me is weird because it seems very straightforward. But if you look at different definitions on different websites, you'll find different things. So I like to just sum it up to if you planned it or if you didn't plan it. That's essentially the difference. So prescribed burn is you sit down, you planned it, you get a burn permit or anything like that, and you say, today we're going to burn this fire. That's a planned fire. Now, when it becomes unplanned is when you say, we're going to burn 200 acres, and then next thing you know, the fire jumps over to another field, and you just burn thousands of acres. That's when it becomes unplanned. So this is kind of something to look at. And a lot of people, while wildfire gets all the accolades and it gets all the news stories, but prescribed burning is, if you see on the slide, it's almost 3 times more of the pollution that's in America. So this is something that most people don't know. So most of the air you breathe that's polluted is from prescribed burning, as opposed to the large major wildfires that happen during a small time of the season. And even though one produces more pollution, one's more frequent. That's kind of a way to think about it. So worldwide, we have something burning every single day, every single second, every single hour, every single minute. This is a weird thing to think about, but as we're sitting here now, there's millions of wildfires happening across the globe. And there's probably wildfires of prescribed burning happening right up the road. There's several places they burn all the time, such as you have the Congo, which burns. You have the Brazilian area, the Amazon. You have Mexico has a lot of wildfires. There's any forest you can think of is going to have a burn cycle. So you can imagine that. And then on the continental U.S., we have typically the southeast has a lot of prescribed burning that occurs. And this is usually a seasonal cycle. And then you have the West Coast always having wildfires that happen all the time. And within that, since you have all this pollution that's being emitted, which is usually the actual issue, a lot of people think that people are out here running away from fires and dying, but that is not really what kills people. What kills people is the air they breathe and how much of that pollution they're taking in. And once you take in a certain amount of pollution over time, it eventually gets to you and overcomes your system. So worldwide, on average, we have about 300,000 deaths per year. Now, it's a large number, right? That number is dependent upon whether it's a dry season or wet season. So El Nino, La Nina for my meteorology folks. So if we have a lot of rain that year, we're not going to have a lot of fire. But the next year we will, because it'll be a drought year. And it can go up to anywhere between 500,000 deaths down to maybe 150,000. So this is just from like smoke inhalation, and this is just from exposure over time. And then for the continental U.S., more importantly for us, it's on average between 5,000 and 8,000 deaths per year, depending on whether it's rain or dry season. And compared to other things, fire is still not really the bigger killer for folks, but when it comes to air pollution, it is kind of high. So, and again, these numbers are growing. This is something else we like to tell people. This is not a problem that's going away. This is not a problem that will go away. This is not a problem that necessarily should go away, but we have to figure out how to deal with it in a way to make it safer for humans, especially on the prescribed burning side. We can't really do much about wildfires outside of burning those areas before they burn in the big fires. But this is something we have to try to work to deal with. So again, what we do to keep humans safe, as well as to monitor these fires and to keep things going smoothly, is we've progressed since the early years, where it used to be if you see something, say something, which is not the most effective way of fighting fire. So they got a little smarter, and they just put a big tower up. So essentially, like, think a ladder. You go on top of the ladder, and you sit up there all day, and if you see some smoke, you tell someone, and then they go find some friends to go try to put it out. We've gotten a little better than that. So now we use airplanes, we use satellites, as Chris mentioned earlier. We use LiDAR systems. So these are like little laser beams that you can point at smoke or point at the distance, and you can tell when the smoke is thickening up what's going on. So we're working on trying to figure out innovative ways of detecting these things quicker. Because if you detect it when it's sort of like 1 or 2 acres burning, you can put it out before it gets to 100,000 or 10,000. Because a lot of times, once it gets to a certain level, you can't do anything to stop it. You just have to contain it. And we're also concerned about firefighter lives, because you're sending these folks out to fight these fires, and if it's a raging blaze of 100,000 acres and you're in front of it, you can't really do anything about it. So we have to keep those folks safe as well. So kind of to get into what I do more or less, I'm a fire modeler. That's essentially the title. And with that, kind of give a brief, we have the detection method. So kind of what I talked about in the previous slide, you have to find the fire and you have to put that into this black box per se. So that's a lot of math, physics, chemistry, all this stuff goes into this black box. So math and stuff is what I call it. And with math and stuff, you get this fancy output. So you get this nice prediction of where the fire is going to go, how it's going to spread, who's it going to impact, where the smoke is going to go. You get all these different things that come about from that. And with that, you can essentially get the answer, what you think is the answer. And again, this should be the end of the talk, right? We have the answer, we wrote these fancy models, we have everything. But there's some issues with that. You have to worry about how wind is input into your model. Do you have the right meteorology? You have to worry about what is the size of the fire. Did you detect the actual size, or did you detect what you thought was the size of the fire? Was it 10 acres? Was it 10,000 acres? This all changes in your model. And then you have to worry about what was burning. You know, was it trees? Was it plants? Was it someone's house? Those things. Then you have to have, how long was it burning? Was it burning for 4 hours? Was it burning for 2 hours? Burning for 10 days? You have to worry about the rate of spread. How fast was it burning? Was it burning 100 acres per minute? Was it burning 100 acres per hour? You know. And then you have to worry about the intensity. How hot was it? Was it 1,000 degrees? Was it 400 degrees? These are all things that struggle. And then you have a bunch of things like convection. Was it wet? Was it dry? Was it, the plumes stay together? Did the plumes separate? You have whether the plume went up into a certain layer of the atmosphere, or whether the plume stayed below. You know, you have a bunch of different things you have to worry about that lead into issues such as plume rise and transportation. So how far is this thing going to go? What community is going to impact? Is it going to impact me, or is it going to impact my neighbor that's 2,000 miles down the road? Because you have fires that can go all the way in the stratosphere and travel across the world, same as a volcano could, all the way down to fires that if you burn it in your backyard, the smoke is going to stay in your backyard. So within that, you try to figure out how to model that. And that's kind of what we try to do. So I'm going to give a brief example of a modeling experiment and how these things can lead to studies of human health and studies of epidemiology and studies of financial and burden of fires. So kind of what we did is we take that black box I spoke about earlier with all our models and stuff inside of it, and then we can say, okay, so here you have the fires, and you can take them out of the model. Since the model, you can essentially put things in it, and you can take things out of it. So what we do is we essentially say, run the model without fires, and then run it with fires. And we want to figure out what is the difference. And what you can see is you still have the Ohio Valley pollution that we all know and love, since I'm from Kentucky, of course. And you see all those folks, we're always dealing with those power plants, those energy generation plants. But when you add fire, you get other folks that are also just as impacted. As you can see the red on the figure in the bottom left, it grows when you add fire. So it shows that fires are contributing in a large way to our pollution. And then what we can do further, since we're running a model, is say, let's look at only the fire impacts by itself. And when you do that, it's an even clearer picture that the areas where fires are impacting are in the southeast, so that bottom right, and then you have areas in the Pacific Northwest. So in this particular simulation, it was 5 years, and we had some particular large wildfires in California as well as Idaho, and they pop up very clearly. But the problem is these prescribed burning for us, in particular in North Carolina and the Georgia, Florida area, to where this is a constant signal that happens over time as well. So just the same as we might see on TV, all those crazy wildfires out in the West Coast, we have just as much pollution here. So this is something that folks have to be aware of, and this is stuff that we're working on to make safer. So within that, we can talk to our folks at the hospitals as well as epidemiologists who can look at hospital visits and why people were there, and hospital deaths or deaths that were declared and what happened to those folks. And within that, we can compare that with our model data using counties, cities, all the way down to zip codes or census data. And we can figure out who's being impacted, how they're being impacted, and what's happening to them and why. And we've zoned in on this particular study using the wildfire model simulation that I just showed. And we just overlaid that with where people are dying and why they're dying when it's like health related. And you can see here, there's a lot more deaths in the southeast area based off wildfire pollution than there are on the west coast. And this is because there's a pervasive constant signal that's happening from the smoke. So this is kind of something that we have to deal with again, and we're trying to find safer ways to do it. So looking kind of in depth into that type of data set, you can see that the type of cultures that it impacts. So you can see that for Asians, Black, Native American, and whites, when you break it down into different categories, who's being more impacted? As you can see, this is not population weighted necessarily, but you can still see that 81% for whites and 13% for blacks. It kind of matches what the population numbers are. So that's kind of an interesting part of that thing. But when you try to take the difference between those population sets that are living in areas that are affected in the top 25% from purely wildfires, as opposed to areas that aren't, you can see taking the difference that the African-American population is at 5% affected, as opposed to the whites who are at -6. So what this is saying is whites are less percent chance of being affected by air pollution from fires as opposed to blacks or the other categories, which you can take with a grain of salt on what that's good or bad or what that means. I'm not a person who studies that, so we don't look at that. But next, since we understand that talking to people about how things impact people is not always the best way to enact change. So we know how to enact change is to speak about the monetary value of something. And at least from my perspective, if you know how to do it any other way, please tell me at the end. So what we do is we look at per year how much fires are causing damage in a monetary sense. So this was done with $2010. And what you can see is, on average, the short-term health effects, which is your hospital visits, your burned houses and things like that, and your deaths, are about $13 billion per year. And on average, the long-term effects, which is the deaths that happen downwind, like the 10, 15 to 20 years, that is costing us about $100 billion a year. So with that being said, this is motivation for studying these things even more. So kind of further, we talk about what I'm doing. So this is kind of the experiment we did where you can kind of see these smoke plumes and how they evolve. And this is not I show a video at the end, but this is kind of how they look when you're out in the field. These are small fires that are like maybe 30 acres. So if you would think of an acre, you probably live on a quarter acre of a house for your apartment or whatever it is. So just multiply that up and think of small fires such as that can produce smoke that can be seen from miles away, or that can be breathed in from miles away, depending on the meteorology. So this is why we have to understand these things even better. And so here's a recent experiment we did in that same field where you can kind of see using satellite technology as well as LiDAR technology how these smoke plumes are evolving over the day. So this is showing one day on the 17th of March in 2010, where you can see kind of how this is the boundary layer I'm following with the marker, and then you can see the plume heights kind of drawn on there. And with that, the importance of doing experiments is so we can drive the models, because it's extremely expensive to set up these experiments. Even though the experiments give us closer truth to the answer, the models allow us to do it more frequently, to test it, to try different things, to figure out what's wrong with it, what's right with it, and to figure out when we should and should not burn, and what would be better to burn, what months are better to burn in, because there's certain process on this planet that in order to prevent them from happening, we need to burn. So this is why we want to use model development to drive the experiments, and vice versa. We want to use these experiments to drive the model development. So what is shown here is kind of an experiment I did where I used two different plume height schemes, which essentially is the vertical allocation of the smoke. So how high the smoke is going to go and who the smoke is going to impact. And what you do with that is you can look at these red dots or squares, if you can actually see the shapes, and those are the measured heights. And a lot of times we don't have the measured heights when we're modeling. So usually you're just saying, this is my best estimate. But with these experiments, we know exactly where the height of the plume is. We've seen it, we can test it, we know. So we can run our model against those experiments, and we can tell from there how good we're doing. We can kind of do a fact check, more or less. And what we can see here is that some things pop out. So if you see this gray smoothed outline, this is just how the emissions were spread in this particular day in the model as is. And now, from the naked eye, without looking into anything, without knowing any science, you could probably tell in 5 seconds that that gray smooth line is not where these red dots are. And that's essentially telling us we have a problem, right? So with that, we can do some tweaks to the model, and you can see this new curve that pretty much shows we're getting closer to what that answer should be. And we do things such as switching to temporal allocation, which is shorten the time frame. So we know that not all fires should be treated the same. That sounds easy, but when you're writing a model situation, you have to do something in general. But we know that we can separate different cases out to simplify things and to make it to where the model can still give us some useful information that's closer to the answer. So that's what we do there. So in future work, we want to continue doing more field campaigns, continue getting support for those, and we want to have more satellites coming up. We have Tempo, which should be coming online in 2021, hopefully. And that should be the first air quality sensor that's going to be released by NASA, the first satellite purely for air quality. So this will be a really big thing, and this will really help us out. It's going to be a 4-kilometer resolution, which is higher than a lot of sensors that are out there now for air quality. So this will help us improve our models as well, and this will help us essentially get close to the right answer to keep you guys safe. And we want to do more laboratory experiments to where we can figure out what the smoke is doing, what's in the smoke, how high the smoke's going to be, how it's going to affect people, what's the chemistry of it, and how to best prevent it from getting into our lungs. So there's some cool stuff that's coming out to where they can filter the smoke before it comes into your house. So a lot of times people are in these fire-prone areas, they can't necessarily just move. It's not always easy to just uproot your whole family. But if we can put something on your house to help prevent you from breathing in unhealthy smoke, that could help out some folks. So I'd like to thank everybody for coming out, my colleagues, co-authors. So appreciate you guys. So we have a cool video. I don't know how to play it, but do you know how to play it, Chris?
Hit the advance it one more time.
Oh, it's going. Okay, cool. No, forward too far. Okay, it's playing. Oh, here we go. It's playing. Okay, so this is kind of from the March 2017 experiment that I did. And I just want to give you guys a glimpse of what it looks like to see these things. Oh, the sound's on. I'll shut up for a little bit. Okay, so yeah, the minute video is pretty short, but if you guys want to see more video, please contact me. I can send you more. But the point of that video is I'm trying to be the connector, more or less, right? So you have people who only do experiments, people who only do modeling. I used to be on the sector that only did modeling. So recently in my career, I've been transitioning to doing both. And what I've realized is that as a modeler, we didn't really talk to experimentalists. So you have people who are designing these experiments that don't know what the modelers need. And you have people that are designing the models that don't understand what needs to go into it. So a modeler would take a number from an experimentalist and believe it 100%. The experimentalist would take a measurement and not believe it at all, but has to pass it to the modeler. Because if you're the one designing the thing, you understand what's wrong with it, essentially. It's sort of like raising your own kid. You know what's wrong with your kid. You know how your kid acts. And someone else seeing your kid is going to think, oh, this is a great kid. They act nice around me. So that's kind of the way to think about this. So I like to show this video because it was the first time I was seeing a fire up close, outside of like a house fire, things like that, and just feeling the energy and the heat and the power of a fire that was only like 30 acres large. And we saw like little tornado vortices that developed. We felt the heat coming off of it, and you can hear the wind. There was no wind on that day. That was all wind generated from the fire. So this is something else that trying to model these things without seeing them firsthand is difficult. It's difficult enough, but it's even more difficult not being out there. So this is what, I think people need to see and understand and get appreciation for these things and what the firefighters are doing when they're fighting to save your lives and my life as well. So thank you.
Thank you very much. So now we'll swip over to audience Q&A. We've got several more minutes left. Yes, we got time for a good discussion to light up here. So if you've got questions, nobody laughed at that fire pun. So if you've got questions, wave at me. I've got a mic. Anu has a mic there in the back, and we'll get to as many as we can. If we don't get to you yet, just keep throwing your hand up, and we're going to try to get to as many people as we can tonight. I'm going to start over there on my right side of the room.
Thank you so much. It was a great talk. You mentioned that fires have gone up by 50%. What are the reasons for that? Is it just more people living in more areas, starting more fires accidentally, or is there something else behind it?
That's a very fun question to answer. So it has to do with the changing of the climate, right? So you have more exaggerated seasons. So you went from a short period of drought mixed with a short period of rain to longer periods of drought, higher temperatures, things like that. And with higher temperatures and longer periods of drought, you get more fire that happens in places that it normally wouldn't happen. So you have places that normally on a cold or don't get up to the hundreds of degrees or 90 degrees for, like North Carolina gets full weeks of 90 degrees. That's something that's changed from back in the day, right? So this is, as the temperature rises, you're going to get more of that to happen. And then you have deforestation that happens to where these buffer zones that normally occur to stop fires from raging over to other places are being removed and replaced with buildings. So for example, in Gatlinburg, Tennessee, where that big fire happened, there should be no buildings there. It's the middle of a forest, right? So we're taking over these places and putting buildings there. And you have areas like Seattle, Washington, where they literally have to tell people, you can't build a house within 10 meters of a place that we know is going to burn because we won't come get it. But people still build it there. You can't stop people. So this is another reason why structures burn more, and this is another reason why fires are growing. And there's a whole slew of reasons, but those are just kind of some.
You're next.
Hi. It really was very interesting and new to us, who something completely different. First, I wanted to just underline the thing you said at the end of your talk about the importance of people knowing both the modeling or the analysis part and the data collection part. So often these days, with the availability of huge and great data sets collected by government agencies and the like, the people doing the analyses have no experience with collecting the data. They don't have a sense of the quality of the data, the flaws. It's very dangerous when people lose track of the data collection part. So anyway, that's just editorial. The question I wanted to ask has to do, though, with the modeling, the black box that you didn't get us into very much. Just to give us a little bit of a feeling for what's going on there, can you tell us about controversies in your field just maybe one or two controversies, disagreements among people who do the modeling about, how these models should work. What are the issues that really get people hot?
Okay, so almost every issue gets modelers hot, right? So you have several different leading teams that develop air quality models. Like the EPA just has one. We do CMAQ, which, that's our model in the house. And then there's a Harvard group that does one. There's a Berkeley group that does one. There's the Forest Service has their own. NOAA has their own. So there's 1,000 different ones. Just to give you an example, just to measure something similar as temperature or the boundary layer height, there's probably 20 different schemes that you can put into each model just for those one things. And I mentioned briefly plume rise. Currently, there's no agreement on plume rise and which one's the best. So that's kind of a hot topic right now currently, trying to figure out just if you burn something that's this size for this long, how high will it go? No one agrees on how to do that. So that's kind of give a sense of these things have been developing since computers have been developing. So you have to understand computers haven't been around that long. So to run a model simulation within the last 50 years essentially has been growing. So we're getting better, and that's why we need to do more experiments and we need to get more agreement on things. We can't even agree on how to name something. Like if you look up different definitions of wildland fire, you'll find a different one on different websites. So if you can't get the definitions of the word right or agreed on that, how do you think you're going to get scientists to agree on different things? Like we all know that things should be studied and we all know that things exist, but how to solve it, there's millions of ways. Like if you solve a math problem, same idea. You can solve 2 + 2 1,000 different ways, but it's the same answer. It's right or it's right. So we can talk more later. Yeah.
Hi, great talk. Two questions. First question, last week here in Raleigh, we had, hazardous air quality from fires that were in Canada. Can you talk a little bit about that fire? Because I didn't hear any details about it. I just heard that we're getting smoke in the air from Canada. I don't know if you know about what that was. Second question is, you mentioned NASA satellite. I do work for NOAA, and I was wondering, is NOAA a lot of the GOES-R, for example, are those the satellites that you're getting your data from? So the 2 questions.
Yeah, so to answer the first question, second question first. So all the groups typically work together. So all the satellites, all the groups contribute in some way for the most part. It just NASA gets most of the credit because they're the satellite people. So we pass work to them, NOAA does the same way, and that's how that typically goes. And when it comes to the plumes going from one area to the other, it's kind of what I mentioned with that plume rise, plume height thing. You have to think of, if you think of volcanoes, right? You have this huge injection of smoke that just comes up and it stops at a certain layer. And then some of it continues to go. And it depends on what layer it goes. It's essentially when you look at a weather map in the morning and you see how it's showing you these airs coming down from Canada, it essentially takes the same route as that. So this is essentially what we're trying to model. And I've seen some studies to where smoke and fire from Alberta, Canada, has came all the way down to Houston, Texas, and caused 2-3 days in a row of just bad pollution. And it can go up to 100 parts per million when normally it's around 12 or something. And this is another thing that the EPA has to deal with, because cities are like, hey, don't fine us, don't yell at us, it's not our pollution, it's coming from somewhere else. And they do these things called exceptional events demonstrations, to where you can run a model and say, hey, the air came from here, this fire was happening, or this power generation plant was over here, and that's what caused bad air over here for your monitor that you measure. So it's kind of what started my PhD career, because there was a huge fire that happened in California in 2013, and that air polluted St. Louis, where I was studying at. So we were taking measurements there, and I was like, why is these wacky numbers happening? And it turns out when I ran a model, it came from a fire in California. So this is kind of,
it might be my imagination, but it seems like when they have big fires in California, if the winds are above 50 miles an hour and the humidity is below 50% and it's in the mountains and it hadn't rained in 2 months, they never get it put out until either it rains or the wind stops. Would you want to comment on that?
well, yeah, pretty much. Because the problem is, once it gets going, it's pretty much nothing you can do. And a lot of times there's been theories of argument, a lot of arguments about whether we should just let it burn. But the problem with that is you can't just let it burn if someone built their house there, right? So if you have like a city like Beverly Hills, for example, where all these millionaires have their homes. Like, there was a recent story where, like, Oprah, I think her house was affected, right? So you have Ellen, whose house was affected as well. And you have these billionaires, millionaires, they're going to tell you to fight this fire. And we also don't want to lose human lives. So like the Gatlinburg, we've sent firefighters out there. The best case would just be move out of the way, let natural cycles do what natural cycles do. But as you know, humans like to be where humans want to go. You really can't stop the fire.
Again, wave at us if you've got questions. I know there are more hands, but we want to make sure we get to everybody.
It's an interesting talk. This is sort of a question about putting together a few of the other questions that were already asked. But what kinds of data sets exist that you use as input to the models? I noticed on some of the maps that, for example, political boundaries like Kentucky and Alabama stand out, which leads me to believe that there's differences in the quality of the data you're getting from different places. So what kind of data sets exist, and maybe what's their resolution?
Yeah, so I kind of mentioned it briefly in one of the slides that, and that's also part of the problem, right, is that there's so many different data sets. Everyone has their own data set that they develop, and we develop one in-house called the National Emissions Inventory. And then there's fire emission inventories that are developed from different people. There's this thing called GeoMac, which just does a perimeter around the fire that was burned. There's smoke reports to where people are just saying, I burned some in my backyard, here's how many acres I burned, all the way up to the satellites detecting fire. So, and then you have, that's just the detection of the fire. And then you go all the way up to, you know, how many acres were burned, how long did it burn, all these things that have different data sets for. And sometimes they're congealed into one coherent data set, but everyone does that their own way. We usually use the U.S. Forest Service for our particular data sets, and they have this whole framework called the Blue Sky Network, and they just put all these different data sets together, and we take that into our model and then run it from there. And you see how the problem can propagate, right? So like if you tell me I'm going to burn this many acres on this day and you don't do that, and we put it into our data set, there you go.
Hi, I have a question myself. So I am wondering whether, when I think of wildfires, I think of lightning striking like some kind of just prairie. And I'm wondering if the cultural representation of fire in the quote-unquote wild is actually how fires are started, or how are all the different ways can a fire start if it's not directly related to a human, like throwing a cigarette?
Yeah, lightning is the main way. That's pretty much it. Yeah, just lightning or something that causes a spark. One of my favorite ways that I learned was smoldering cow pies.
Oh, okay.
It's a big issue in Kansas, right? Okay. So, yeah, one of the researchers there, he told us that he had like burned a field, prescribed burning, right? And there was a bunch of, bison there. So of course, bison defecate, and some of those things smolder for hours on end, weeks on end, and then the wind blows it, and it rolls over to someone else's field, sparks up a flame, and therein lies a wildfire. Yeah, no one's seeing it, no one heard it, no one knew it happened. You wake up the next day, 10,000 acres gone.
Interesting. Cool.
Again, wave at us if you've got one. All right, we'll get a microphone to you. But I'm thinking fire to me is something that seems totally unpredictable. Like you're trying to model something that is wild and crazy, and even a backyard fire, I grew up being taught, keep like a bucket of water and the hose pipe because anything can go wrong. And there are billboards on Interstate 40 talking about an ember can travel a mile and start a fire somewhere else. So I'm having a hard time even wrapping my head around putting this down into a mathematical equation, something that I think strikes fear into a lot of people, and just because it seems so unpredictable. How do you wrap your head around those concepts?
Well, for one, I just like fire, right? So, and then the easiest way to think about fire is to think away water, right? So you have fluid. So we treat it with the fluid dynamics equations, essentially. So if you guys remember physics or math, it's essentially the same thing as like Navier-Stokes and all these type of linear equations. So you have a mathematical model that essentially says you have something here, and it's this much of that something. Here's the equations on how things are supposed to move based off how energy is conserved, created, destroyed, matter operates. And then from there, you can figure out point A moves to point B. And you can essentially say, if I have this much at first point, these are the equations that show me how it's supposed to get to the next point, run that. And the way we do it in the model is you say, if I have experiments or examples that show me where it's supposed to be at time 10, which means 10 minutes later or an hour later, if my model is off, then just nudge it back towards that answer. And that's essentially what meteorology is done. When you see the weather on the map, they run these big models and they say, okay, the temperature here, according to this observation, is supposed to be 10 degrees cooler. So nudge the model towards that. And that's how we can try to make things easier. I mean, it's a very difficult process, but you can simplify things. And that's part of the reason why the process is not exact science, because you're approximating these solutions. Like a lot of these equations you can't fully solve, but you can get an approximation for them. And we get that from our math friends. And they do all that fancy work, and then we just put it into the model. Yeah.
Hi, thanks for your presentation today. I was just wondering, can you clarify what are the purposes for all of the planned fires? Is it for future fire control, or is it agricultural? Why all these planned fires, and who are setting these planned fires?
So that's a loaded question, but it's the simplest way to look at it is, okay, when you have the major wildfires that you see in the West, where you see these huge crown fires at the top of the treetops that burn it off and stuff like that, those are the definition of wildfires, right? So what they do to prevent those from happening when they don't want them to happen, or on an off-cycle year, they burn all the stuff that falls down from the tree. So the leaves, if you think about that, the pine needles, all this grows on the forest floor. That stuff, once it gets dry, can spark up really easy. Lightning strike quickly. So that's usually how things get started. And then, so the prescribed burn, they burn that. So they send a fire through and essentially burns all the base. And then out here in the southeast and in Kansas, for example, it's a lot of agriculture use. So like I mentioned for the grass, right? So in Kansas and around the Oklahoma area, they burn it pretty frequently. So once the cattle graze and they eat all the grass, they essentially burn all that grass off. And the roots, it essentially grows back in like 2 weeks, and sometimes less than that. Like we were on a 2-week experiment, and the first couple fields they burned, before we left, they had greened back up. So I mean, it's a very common practice. It's been done since the Native Americans were here, and we just essentially just stole their process. So this is something that we're trying to teach people, that just because you historically did it this way, there's probably better ways to do it for the air quality. And that's all. We're not telling people to stop. We're telling people there's better ways to do it. So it's the process you don't want to stop. Because if you let everything just grow up, we're going to have a boatload more fires than we have now. So we have to do some type of mitigation. There's a whole bunch of fire management folks, and we go to conferences for all this stuff. There's a billion different ideas on how to prevent that and how to do it, right?
So with all the different groups dealing with fires, local, county, city, rural, urban, federal land, private land, how does everyone coordinate basics? Like if a federal property is burning and then it's over into a state property, then it's into private property, how do you coordinate techniques? Is there a set standard for all fire groups? Would one group say, no, stop here, let it burn? Another group say, no, my land now, put it out. How do you do that? How do you coordinate that on the ground?
To be honest, I actually don't know. So from what I've seen, it looks like sporadic, horrible, hopefully controlled thing. That's just my preview, right? So you don't really stop it that way because fires don't have political boundaries. We do have some issues when it comes to tribal lands, I've heard before, to where it's like this is literally treated as if it's a different country. You can't just go into their area, right? So like you have stuff like that, but typically if you're talking about Kansas dealing with, Missouri, it's not a problem or something like that. But a lot of times they create these fire teams. So they say, we're going to bring some folks from the EPA, Forest Service, or volunteers, and we're going to have a team that's set to fight this particular fire. And then everyone just gets on board and does what they need to do. So that's what I've seen from my small view. I don't usually fight the fires. I just model them. So.
Thank you.
I have a question. You mentioned equipment that could go on houses that would help improve air quality. Is there any other practical application like that that you can talk to? New technologies that are coming forward, or any other results of your work?
Yeah, so that's mostly my colleagues that deal with the epidemiology and the health stuff. I'm mostly just the model side. But from what I've seen is that they're trying to develop sensors that can be carried on like a cell phone. Like there's an app that they're developing called Smoke Sense, to where you can tell, hey, I'm smelling this air, I'm receiving this much pollution, you know, what can I do about it? And then there's HEPA filters to where you can filter out the air that's inside your house and things like that. The EPA is developing stuff and working with folks to do that. But that's pretty much brunt of what I know with that, yeah.
Let's give him
Hopefully it gets better.
I was going to say, let's give him one more round of applause. Great stuff. Thank you so much. Appreciate it. Thanks for coming out. And, hey, thanks to all of you for coming out to the Science Cafe tonight. Did you learn something new? I hope so. I hope you've got something new to take home, something to think about on your way home tonight and through the rest of the week to at least get you to next Thursday at 7 o'clock, when we'll be right back here at the Daily Planet Cafe and we'll learn something else new. Check out naturalsciences.org for the schedule of events to see what's coming up. There's always great topics here in the Science Cafe. Thanks for coming out. Good night, everybody. Appreciate you.